Hello everybody, welcome into another lesson. So today we are going to talk about parametric equations and their graphs. Now, parametric equations are called that because you have a parameter that x and y are based on. That parameter is called t, where t is your independent variable, usually time. But that relates to what the x motion is and the y motion is at that given time t. So you could say at any given time you could have a horizontal motion, your x-axis, and then you also have a vertical motion, your y-axis. This is particularly useful in physics where you might try to figure out the horizontal motion of a particle at a given time, or vertical motion if you're launching a rocket. And there's plenty of other applications, but those are the two biggest. But this accounts for what each the vertical and the horizontal is doing at a given time t. Now what you can do is something called elimination of parameter. You can do that and you can actually convert these parametric equations into one rectangular or Cartesian equation. How you do that is you solve for t in terms of x, and then you're going to take that value of t in terms of x, substitute it into your y equation where you see t, and you'll get y equals a function of x. So let's get started with some examples. So let's say x equals t, y equals negative 4t. So x equals t, y equals negative 4t. Well, one way to do this is you can set yourself up a table of values for t, plug in values for t, and then you'll get your respective x and y coordinates. Or you can go right to eliminating the parameter, which might make your life a lot easier. And some of the equations we're going to do today, you'll be glad we're doing the elimination of parameter first. Well, we know x equals t, which we could say then t equals x. Now all we have to do is take that x, plug it into our y equation. You would literally get y equals negative 4x. That's how easy it is to convert these into rectangular or Cartesian equations. This turns into y equals negative 4x, which would just be a line. Let's go ahead and graph. So when x equals 0, well, y would equal 0. When x equals 1, y would equal negative 4. When x equals negative 1, y would equal positive 4. And I think we can clearly see we're going to get a line with a slope of negative 4. So there is your line, y equals negative 4x. Now had you set up a table value for t, x, and y, set up a table of values, you would have arrived at the exact same thing. It's just a longer way to get there. My suggestion is when you're graphing these, eliminate that parameter first, and then you can have a nice simple rectangular equation to work with. Alright, let's do another one here. So we have x equals 3t minus 3, y equals 2t plus 1. So as we see at a various time t, we have different motion for the x and the y. But we can convert this into a rectangular equation. How do we do that? Once again, solve for t in terms of x to eliminate the parameter. If x equals 3t minus 3, well that means that 3t minus 3 equals x. Let's solve for t, so then this will turn into 3t equals x plus 3, which would give you t equals 1/3 x plus 1. So now we've solved for t in terms of x. Let's go ahead and stick that t into our y equation. So y would equal 2 times that value of t, which was 1/3 x plus 1, then plus that 1. So you'll end up getting 2/3 x plus 2 plus 1. So to simplify, you'll get y equals 2/3 x plus 3. So that's going to be another line. Y equals 2/3 x plus 3. Well, let's pick x equals 0. You would just get a y coordinate of 3. X equals positive 3. You would get 2/3 times 3, which is 2. Plus 3 is 5. So when x is 3, you're all the way up at 5 for your y coordinate. And then if we pick negative 3 for x, 2/3 of negative 3 is negative 2, plus 3 is positive 1. So you'd have the coordinate negative 1, 3. Let's go ahead and connect these dots here and draw the graph. And there you go. You have this line of y equals 2/3 x plus 3 based on these two parametric equations. And again, if you set up a table of values for t, x, and y, plugged in individual values of t, you would eventually arrive at this graph. It would just take you a little bit longer, sometimes a lot longer. All right. Now, what about if we do let's say x equals 1/4 t, y equals t squared. So all of a sudden we have a quadratic on the y, but a linear on the x. Well, the process is still the same. Why don't we start with eliminating that parameter t? If x equals 1/4 t, that means that 1/4 of t equals x. So then t would just equal 4x. So now we have t in terms of x, t equals 4x. All we got to do is take that value of t, substitute it into our y equation. So y would equal that quantity of 4x raised to the second power, which simplify would give us y equals 16x to the second power. So yes, you have a quadratic equation, which is going to be a parabola. Let's pick x equals 0. If x is 0, of course, you'll get the coordinate 0, 0. Why don't we make each of these worth 2 units? Yeah, let's make each of these worth... no, let's not do that, actually. Let's keep each of these worth 1. There's a reason. What if I pick x being 1/2? Well, what if it's... so we take 1/2 and square 1/2, you get 1/4. Okay, so 16 times 1/4 is 4. So when x is 1/4, you'll get a y coordinate of 4. When x is 1/2, rather. And then if I picked x being negative 1/2, I would get the same thing. I would get positive 1/4 times 16, which would end up being 4. So I'm going to get a very skinny looking parabola. I will have a very skinny looking parabola at this point. So that would be y equals 16x squared. And that's based on these two parametric equations. All right. Now, what if I gave you something like this? X equals e to the negative t, y equals e to the 3t. And your first thought is probably going to be, this is going to be some exponential equation. Well, you're going to be surprised what happens when we eliminate the parameter, how this is all going to relate. And I think it's safe to say you probably do want to eliminate the parameter in this case, because if you sit there and try to make out a table of values for t, x, and y, you're going to get e to so many powers, which are going to give you some awful decimals. So this is where eliminating the parameter is particularly useful. So we know x equals e to the negative t. Well, that means e to the negative t would equal x. Now to solve for t, since t is a power, e's our base, we need to take the natural log of both sides. So if I take the natural log of e to the negative t, I'll get that equal to the natural log of x. Natural log of e to the negative t would just give me negative t equals the natural log of x. So t equals negative of the natural log of x. So we've solved for t in terms of x, but we still have to stick this into our y equation. So y is going to equal e to the 3 times that negative natural log of x, which we could start by simplifying that as e to the negative 3 natural log of x. Now, what is a property of logs? You have a coefficient on the logarithm. That's the same thing as the log of the quantity raised to the power of that quantity. So this would be the same thing as e to the natural log of that x to the negative 3rd power. The reason I did that is because now we have e to a natural log. Your e and your natural log will cancel out. You'll just be left with that x to the negative 3rd, which means y is going to equal 1 over x to the 3rd power. So really and truly, you don't have an exponential function, you actually have a rational function. But we do have to restrict the domain for one fact, that x can't equal 0. If you put in 0, you'll get an undefined expression. And earlier, before in previous units, this was also called a vertical asymptote, when x equals 0. So let's go ahead and graph this function here. So let's pick x equals 1. 1 over 1 cubed, well that just gives you 1. Let's pick x is 2. Well, 2 cubed is 8. 1 over 8's 1/8. So you'll be about down here. Now, what about, let's pick 1/2 for x. 1/2 cubed is 1/8. 1 divided by 1/8, that's actually all the way up at 8. So let's go ahead and start this graph here. And there's what it's doing to the right of x equals 0. Now what about the left? Let's pick x equals negative 1. Negative 1 to the 3rd power is negative 1. 1 divided by negative 1 gives you negative 1. Now what about when x is negative 2? Negative 2 to the 3rd is negative 8. 1 divided by negative 8 is negative 1/8. That'll be about up here. Let's pick x as negative 1/2. Well, negative 1/2 to the 3rd power is negative 1/8. 1 divided by negative 1/8, that just gives you negative 8. So you'll be at negative 1/2, negative 8 for that coordinate. And here's what your functions do on the left. It pretty much looks like a typical rational function. It's only stretched a little bit more because you have x to the 3rd in the denominator as opposed to x to the 1st. But there's the graph of y equals 1 over x to the 3rd. It's the exact same thing as if you took values of t, plugged them into x and y, and got individual coordinates. Only it'd be a much more hideous way to get there. Alright, so far we've had the full domain in effect. Now, what about when you have restricted domains? So, in other words, they give you t the domain of t is restricted, what are we going to do then? So x equals t, y equals 1/2 t. And we're only going to consider t from 0 to 5. So 0 is less than or equal to t, which is less than or equal to 5. We're not considering anything to the left of 0 or to the right of 5 for t. Well, the process is still the same to start with. Eliminate your parameter, get t in terms of x. And then put that into your y. Well, if x equals t, that simply means t equals x. So we can plug that value of t in for our y equation. You would get y equals 1/2 of x. So this turned into a nice linear equation. Now, when your domain of t is restricted, here's the thing about that. You have to plug in those values of t to get your actual domain for your rectangular function. So the domain's always based on your x value. So plug in your left endpoint for t being 0. Well, that would also give you an x value of 0. And then if you plug in 5, in this case, you would also get 5. So in this case, it worked out for the domain of the function being 0 to 5. But that's not always true. Now to get your range, just take those values of your domain, stick it in for x. The left endpoint being 0, well, that would still give you a y value of 0, but your range is going to be, if you stick in 5, your range would only go up to 5/2, or 2.5. So the domain of this function in this case is only from 0 to 5, the range is from 0 to 5/2. So let's pick x equals 0. Of course, you'll get the point 0, 0. Why don't we pick, let's see, x equals 1, you would get 1/2. X equals 2, you would get 1. X equals 3, you get 3/2. X equals 4, you get 2. X equals 5, you get 5/2. And that's actually as far as you can go. In this case, you're not going to have a full line. You don't get a full line because you only go from when 0 is less than or equal to t, which is less than or equal to 5, which in this case turned the domain of your rectangular function from 0 to 5, your range from 0 to 5/2. So you have to stick with the domain and range of your rectangular equation when graphing these. So your line only went so far. Okay. What about... All right, let's again say... yeah, let's do this. X equals t, y equals t to the third. So x equals t, y equals t to the third. And we're going to take -1 is less than or equal to t, which is less than or equal to 1. So we only care about when t is, when -1 is less than or equal to t, which is less than or equal to 1, so t from -1 to 1. That's the domain of t. Well, first thing you do, again, eliminate that parameter, get y in terms of x. So if x equals t, that means t equals x. So then y would equal x to the third. So you're going to get a classic cubic function. You'll get y equals x to the third. Now, the difference is t only goes from -1 to 1. So we're not doing the full graph of the cubic function. So to get our x value, the domain, stick in the left endpoint, -1. Well, you would get, of course, -1 for the left endpoint of your domain. Stick in +1, you would get, well, +1 for the right endpoint of your domain. So the domain of this function goes from -1 to 1. Now we can find the range the same way. Well, find the range by sticking those x values into your rectangular equation, you would also get a range from -1 to 1. So let's start when x is -1. You would get y equals -1 to the third or -1. Pick 0, which is in between, you would get 0, 0. And then when x is 1, well, that would just give you y is 1. And the cube function goes something like this. You're just only going to go from here to here because your domain is restricted. We can't graph the whole thing because your domain is restricted, but that's what happens when you restrict your domain. Let's do one more. Let's really change it. We're going to only do one more example, then we'll be done with the lesson. Good one. So x equals t to the third, y equals 3 ln of t. So we've really changed it. X equals t to the third, y equals 3 ln of t, where let's go from, let's see. We'll take 1 is less than or equal to t, which is less than or equal to 8. We'll go from 1 to 8 for t. Well, first thing again, eliminate your parameter. So get t in terms of x. Well, if x equals t to the third, that means t to the third equals x. So t would have to equal the cube root of x. Now, of course, we stick that value of t into our y, so y would equal 3 times the natural log of the cube root of x. But the good news is the property of logs allows us to make this the exact same thing as the natural log of that cube root of x raised to the third power, which would just give you the natural log of x. So this turns into y equals the natural log of x. So we just have a simple logarithmic function. Okay. Now we have to figure out our actual domain for this rectangular equation. So, of course, we need to stick in the endpoints of the domain of t to get the x value, which would be the domain. If I pick 1, I would get, of course, if I pick 1 for t, that would give me an x value of 1. But what if I pick 8 to the third power? That's going to give me a really high domain. So let's take 8 to the third power. That gives me 512. My domain is from x equals 1 to 512. So you see how that changed. I just take my left endpoint of t, stick that in, take my right endpoint of t, stick that in. I get the actual domain of this rectangular function when I stick those in for x. And then I can take this for y. Well, the y is going to then end up being my range. So if I take x equals 1, then of course the natural log of 1 is 0. And then, well, the natural log of 512 is just that. The range would be from 0 to 512. So when I pick x equals 1, I get a y value of 0. And we're definitely not going to make it to 512. No, not even close. I wouldn't have enough room on this board to do that. But let's pick a few values at least to graph this logarithm to make it nice. So natural log of 2 is about 0.69. That's about right there when x is 2. Let's go to 4. I'll take the natural log of 4. 1.39. So 3, 4. That's about right there. Let's do 6. Yeah, let's do the natural log of 6. That's about 1.79. About right there. And I'll do one more for 8. Let's do the natural log of 8. That's about 2.08, so that's a little bit over 2. So as you see, I'm going to get something like this. My range goes all the way to the natural log of 512, which that would give us about 6.24, but that's going to be off the charts by the time we reach x equals 512. So yes, we have a finite range, but we're not even going to get close to it because we're not even going to graph the whole finite domain. And we can't consider anything before x equals 1 because our domain was from 1 to 512. But we know if we were to go left for a natural log, of course, the further left you go towards x equals 0. If you approach x equals 0 from the right, it's going to go towards negative infinity. But that's really all you have because of your domain. But that's it for parametric equations and their graphs. So next lesson's going to open up a whole new world. Some of you may have seen polar coordinates and graphs before, but a lot of you may not have. Now, polar coordinates, so that enables us to take rectangular coordinates such as these, convert them into something called polar coordinates, where we'll actually be using the unit circle to graph on that in the lesson after. And when you do graphs of polar equations, you can get some really neat shapes and figures that you could never get on the rectangular system. So stay tuned for that. I hope everybody has a great day. Take care.